All right, so we need to finish this problem. We did the first eigenvector for the first eigenvalue, that was 75. We need to do the same thing for the second one. So this one, maybe let's do it again in detail, and then the third one, I'll just give you the answer, okay? Because basically over and over the same thing. So for this one, we do the construction of sigma minus lambda I being an identity matrix, which just means that you're gonna put this value, the lambda, into the diagonal of the matrix, no? That's all it means. So that means that we're gonna have here, so let's see, 57 minus 50, 0, 24, 0, 50 minus 50, 0, 24, 0, 43 minus 50, and 1, and 2, and 3, equal to 0. So once you simplify, you get 57 minus 57, 0, 24, 0, 0, 0, 24, 0, and negative 7. All right, so or we can write this just under normal a system of equations would be 7 and 1 plus 24 and 3 equal to 0, and 24 and 1 minus 7 and 3 equal to 0. Okay, so is there any way to satisfy the above system? No, no? Okay, if you want to substitute, if you want, you can go ahead and you can say N1 would be equal to what? 24 over 3 and 3. You substitute over here, you're not going to get an answer, no? Okay, would not be equal to 0. So basically, what would be the only solution to that system would be if N1 and N3 are 0. Okay, so let's say above system is satisfied if and only if N1 equal N3 equal to 0. Okay, so let's see, I'm going back to the notes, see if we can find it here. So I did not mention it earlier. Okay. All right, so in this case, you're gonna see what happened to the solution. So using the normalization condition, that n sub I must be equal to 1. Okay, that's basically, if you want to be the system to be 90 degrees to each one, you need to satisfy this condition, no? Okay, so if n1 is 0, is only satisfied, this is going to be n1 is going to be 0, no? Okay, if n3 is 0, it's going to be n3, 0. But we need to have one that will be 1. So this will mean for n2, so if you want n2 equal 1, then you need to have this one to be equal to 1. So sorry, if I want to be more detailed, can be equal to either plus or minus 1, because minus 1 times minus 1 would be 1, and 1 times 1 would be 1. So the two possible eigenvectors are, so n2 will be equal to 0, 1, 0, or n2 will be equal to 0, minus 1, 0. Let's keep going. Let's not simplify anything. Okay, so now for the third eigenvalue, for lambda 3 will be equal to sigma 1, this sigma 3, we did 75, no, it's lower to high, we did 25. Which one did we do first, the 25? So 25, 50, now we need the 75. This one over here. Okay, so I'm just gonna go, I mean, it's not even a little bit faster, but this will give us what? 57 minus 75, 0, 24, 50 minus 75, 0, 0, 43 minus 75, 0, 24. Equal to 0. So once you do the calculations, you get negative 18, 0, 24, 0, negative 25, 0, 24, 0, negative 32. Or this will be negative 18 and 1 plus 24 and 3 equal to 0 minus 25 and 2 equal to 0, 24 and 1 minus 32 and 3 equal to 0. Okay, so the second equation is going to tell us what? Right away that n2 is 0. Okay? So that means that basically we are only left with this equation here, minus 18 and 1 plus 24 and 3 equal to 0, and minus 24 and 1 plus 32 and 3 equal to 0. If we divide by 6 now, they're all divisible by 6. What do we get over here? We're going to get so it will be minus 3 and 1 plus 4 and 3 would be equal to minus 4 and 1 wait, we forgot, no. So, yeah, no, look here, so it would be, yeah, I have different here on my notes than what I have here, so, okay. So positive and 1 yeah, but it's okay, yeah, hold on 1 second, let's go back for a second here. All right. What we're going to do here is, so 73. All right. Forget this divided by 6 over here. I was trying to be smarter than my notes. All right, so we have this system. So what we're going to do is that we're going to solve first the top one. Okay? So let's say here equation A, equation B. So let's say from A,
It's not negative 24 on the second.
Yeah.
That's where it is.
This,
18.
Equation B is plus
Equation
24
B, yes.
and 1 minus 32.
This is plus 24 here.
Yes.
Okay, this is 24, but this is minus 32.
Yeah.
Okay, anyway, so from equation 1, we have minus 18 and 1 plus 24 and 3 equal to 0. So from this one, you're going to get that n1 should be equal to 24 over 18 and 3, no? Or this will be n1 will be equal to 4/3 and 3. Or, since I did it that way on the notes, n3 will be equal to 3/4 and 1. That way we can select n1. Okay, and the second equation will give us the same thing, but divided by 8, no? Okay, so I'm B here, so let's do it. You see, we'll give you 24 and 1 minus 32 and 3 equal to 0. which basically what is in is that is the same equation, will give you what? N1 equal to 32 over 24 and 3, which is N1, if you divide by 8, will be equal to 4/3 and 3, or N3 equal to 3/4 and 1. So basically they are the same equation, okay? They yield to the same result. So you can either choose A and B. So a possible eigenvector for lambda 3 is what? We could select N1 to be equal to 1. And in that case, what will you have? N3 will be equal to 1, 0, 3/4. Okay? Trying to say that I use the same notation, N1 and 2, yeah, I did, sorry. And 2, I did this, is no bracket, is parenthesis, this one. Okay? So now, normalizing, you don't have to do that, but sometimes it's easier for the calculation if you normalize everything to the same base. Okay, so let's say base 1, so that everything will be to 1. So normalizing to 1, what are you gonna have? N3 will be equal to N3 divided by the magnitude, no? Which is 1 squared plus 0 squared plus 3/4 squared. Maybe I can zoom that. Sure, let me know. Yeah, I could zoom this. Feel better that way? All right, so if you do this, what you get at the end is N3 normalized will be equal to 4/5, 0, and 3/5. But again, this is one possible value. Here you could change, you could put instead of 1 minus 1, no? Okay, it doesn't matter. Like I said before, the eigenvectors is just like the direction of a vector. There is an infinite number of directing vectors for a certain vector, no? Okay, it doesn't give you the magnitude. All right. So now, all right. So the eigenvectors which are the principal stress directions will be what? Will be given by the vector, by the matrix, sorry, n hat will be equal to what? So let's see, the first one that we had in the problem was for, so we have the first one we had here is 3/5, 0, negative 4/5. The second one we find is 0, 1, 0. And the last one we use here is 4/5, 0, 3/5. Okay, and this one, that was, the first one was for, I think 25, for lambda equal to 25, then lambda equal to 50, and lambda equal to 75, no? All right, so each one of those direction vectors. Okay, so it's important here is that there's a property which is important about all these eigenvectors of direction that we said before, is that they need to be perpendicular to each other. Okay, so notice that N1, N2, and N3 are orthogonal, which is the same thing as perpendicular, to each other. So that means what? That N had 1 dot and dot 2. So let's do it. What would you get this one? You will get 3/5 times 0, 0, 0 times 1, 0, minus 4/5 times 0, 0, no? Yeah? Will be 0. Then let's say if you do N1 and 3, what will you get? 3, so 12 minus 4 times 3, 0 again, no? All right? And the other one we need is just N2 and 3. So again, this one is again 0 times a number is 0, 1 times 0, and so on will be 0. So basically, what does that mean? Is that we are dealing with an orthogonal basis. So all eigenvectors are orthogonal to each other. Okay? But that's also true. Remember, on the second eigenvalue problem, we use the notation ni times ni needed to be equal to 1, no? For the normalization. That also did help. Okay. So now, the eigenvector matrix N hat correspond to the transformation matrix Aij. Remember? So remember what was the transformation matrix? Was if you want to rotate one coordinate axis with respect to the other one, you're going to have a transformation matrix. So over here, what does that mean? Is that if you multiply your stresses within this matrix here, you're going to get the stresses in the principal direction, X, Y, and Z. Correct? And why was that important? Because that way you can get the stresses on the direction, on the normal direction where they do the testing, no? So now you can compare the principal stress values to whatever value you get from the table to be the yield stress or the ultimate stress for that material. Okay? So at the end of the day, if you want to be able to compare the stresses to the data, one good way is to find the principal stresses. What is we need to do the principal stresses is to solve the eigenvalue, eigenvector problem. Okay? All right. So in that case, Aij would just be the same equation. So Aij would be equal to, I'm just going to copy the top, 3/5, 0 minus 4/5, 0, 1, 0, 4/5, 0, 3/5. Again, these are important properties, so the eigenvalue, eigenvector problem. All right, and I think this would be the last thing. Right. So recalling that the transform stress sigma ij is equal to, okay, AIM AJN sigma MN, or in matrix form, which is the one I wanted to write really, is equal to matrix A times the stress state times the transpose of the other one. Okay, so let's see if I have space to do it at the bottom here. So what you're expecting this to be equal to then? You're gonna have sigma prime. What is A? A, we have it over here, so it is 3/5, 0 minus 4/5, 0, 1, 0, 4/5, 0, 3/5. Times the matrix sigma, that is equal to, I can deduce it from this one. We just remove the lambdas, will be 57, 0, 24, 0, 50, 0, 24, 0, 43. Okay? I will have it on the page, but just extract it from here, so it will be 57, 0, 24, 0, 50, 0, and then will be 24, 0, 43, times the transpose, so we just switch lines by columns. All right, so we get 3/5, 0 minus 4/5. This will be 0, 4/5. This will remain unchanged. And then this one will also remain unchanged, no? 0, 3/5. Okay, so let's see now if you understood this. What should you get? Remember, this is a transformation of the matrix. And we say each one of these eigenvectors correspond to an eigenvalue. Okay? So what should we get over here? We say we're going to put all the stresses, these correspond to a transformation matrix. So we're going to put all the stresses into their proper direction. Yeah? So what should we get then? We should get only the value of the diagonal, so 25. The next one would be 50 and 75. So basically means that if you have a stress, if you know the stress at one point, it doesn't matter what the direction. If you solve the eigenvector problem for that, the eigenvalue eigenvector problem for that point, once you do this transformation, it will only give you the value now, the new values of the vectors in the principal directions. So basically, let's say in the 3D, these were the values of the stresses, no? 57, 0, 24, 0, 50, 0, 24, 0, 43. You were not able to compare these values to values of the table to know if it was going to be same fracture or not. After you multiply by the eigenvectors, what do you get? Now you get the equivalent, the principal stresses on each one of the principal directions. Now you can compare these ones to the values you have on the tables that come from experiment. Okay? And they are only on the principal direction, X, Y, and Z, no? X, Y, Y, Z, Z. All right? All right. So that is what is very important about this. Okay. Now, this is probably going to answer part of your question. What is the assumption for plane stress, which is what you do almost every single time you solve a problem? So what is the plane stress? It means that one of the principal stresses, okay, sigma 1, sigma 2, sigma 3 is 0. Basically means that you want to break it from 3D almost to 2D, no? Okay? So principal stress, basically what we're trying to do is to remove any type of, okay, we are getting too complicated, any type of shear. Okay, so you made everything on one plane. So when one of the principal stresses sigma 1, sigma 2, or sigma 3 is 0, we have a state of plane stress where the other two planes are designated planes. So this is the proof is I think is part of the homework. So for plane stress, it can be shown that, which is the equation you are familiar with, sigma 1 will be equal to sigma x plus sigma y over 2 plus sigma x minus sigma y divided by 2 squared plus tau squared xy. You take here the square root. So this will be your max principal stress. Your minimum principal stress will be equal to, same thing, but with a minus sign in front of the root. Okay, and then if you want, then there is the maximum shear theory. So it would be principal stresses. For maximum shear theory, you can find that max min, I'm going to combine it this time, would be equal to plus minus so these are principal stresses. Okay, because if it's not principal stress, what should be the value of the stresses? If you don't have the assumption of the principal stresses, what you end up is with all these long expressions over here. Okay? But if you select one of the planes, okay, you want to remain fixed, all right? The equation reduced to these equations over here. Okay? And that's left as part of a homework. I think that's one of the homework problems. All right. So let me see. Do we go now to the delts?